Hi, and welcome to Processing Sound and Sampling. Today we're going to look at controlling and synthesizing audio in processing. So firstly, we need to know basically what are sound waves. Sound is made up of pressure increases and decreases that travel through air. So if you think of a loudspeaker pushing its speaker cone out into space, that creates an increase in pressure. And that increase in pressure travels across space and hits your eardrum where it's picked up. They're pushing waves. So microphones and amplifiers can be used to record those sounds and turn them into numbers, which we can use to store the sound or to apply effects, and then those numbers can be turned back into voltages and made to power a speaker. And when they're powering a speaker, we can reproduce that original sound. Just like we can detect sound using microphones, we can store sound on magnetic tape or on a vinyl record. So the sound that is detected by the microphone is turned into voltages, and those voltages can be used to power an electromagnet here that magnetizes the tape as it passes past the magnetic tape head, so to speak. When you magnetize the tape, you can then pass that tape back past a different type of magnet that listens for magnetism, which creates very small voltages which can be amplified and used to control a speaker again. So that's storing sound using analog methods, storing sound using voltages. No numbers involved at all here, just voltages and magnetism. However, we can use sampling or measurement of sound at different points and turn those voltages into numbers. Now, to record a sound so it can be reproduced, the sound pressure must be measured at twice the rate of the highest frequency to be recorded. So if you want to record a 20,000 Hertz tone, which is possibly the highest sound most people can hear, so that's for a young person who has good hearing, they could hear a 20,000 Hertz tone, or maybe a little higher. For many old people, they can only hear 10,000 or even 5,000 Hertz. You lose your hearing over time. However, a 20,000 Hertz tone needs to be recorded at around 40,000 samples per second, or Hertz. So 44.1 kilohertz or 48 kilohertz recordings are commonplace sampling rates. 44.1 kilohertz is what you get on a compact disc, and 48 kilohertz is a kind of professional standard as well. So here we have that 20,000 Hertz tone, and you notice there's a recording at the top and bottom of each wave form. So if the wave has to go down and up and back to the center, we need 2 measurements per wave. So if we want to record a 20,000 Hertz tone, we need 40,000 measurements per second. If we don't do that, we may end up with alias frequencies here. We're trying to measure the red one, but we end up with the blue one because the measurements aren't happening fast enough to capture the top and bottom of the red one. We're only capturing 1 measurement per wave, and it's not quite enough. Sampling or measurement of sound occurs in usually a nominal range of between 1 and -1. So if you measure upwards, you have to measure increases in sound pressures. You have to measure similar decreases in sound pressures. And the rest point of no sound is 0. It's the air pressure. So sound that is extremely quiet will produce values that are very close to 0, and loud sound will be a big value up to 1 and also down to -1 as well. So you move around that center value. So the 0 value represents the air pressure at rest, so this kind of is at rest. And the 1 is compressed, you can see it's all pushed together here. And the -1 is expanded, and this is a pushing wave across space. For our session today, we're going to use Beads, which is a library for processing that contains functions you can use to control audio synthesis. You can load it from the library manager directly. Examples in this lecture will draw on the Beads library's set of examples, but we'll also have a few extras as well, which I'll make available for you. So now we've sampled our voltages that we've got from a microphone. Back in the day, you used to have to use electronic devices like these to control, to alter the sound. However, now that we have numbers in digital files, we can replace expensive electronic equipment that altered sounds through electronic components with a few lines of mathematics or code. So the lines of code apply formulas to these lists of numbers in these sound files, and that changes the sound and creates new sounds. So similarly, just like you can alter sounds that have been stored, you can also create new sounds by synthesizing lists of numbers. So in this case we have an oscillator, which might be a sine wave generated by creating numbers that go up from 0 up to 1 and back down to -1 and back up to 0 many times per second. So a big long list of numbers with an oscillation occurring. That's passed to a gain control, and we might have an envelope there. We're going to talk about that shortly, where it's multiplied. Then we might have a low pass filter to change the characteristics of the sound. That lets low frequency sound past, but stops high frequency sound. And we're going to talk about different types of filters as well. And then it goes to the output. So first thing to look at is noise. Noise you get when you turn on a TV that's not tuned to anything. You get random noise. It looks like random snow, and you hear a noisy sound over the audio, and it's randomness. So you can generate noise by generating a series of random numbers. These numbers result in sound that has no tonal content, no periodicity, no repetition, just random changes in the loudspeaker's position. So let's have a look at that. I'm going to go to lesson 01, audio context, and open it up for you. Here we have size 300/300. We make an audio context. This is a link to the audio hardware on your computer. We then create a noise generator here. This is a new noise. That's the link to the audio hardware. So it tells this algorithm how many samples should you produce per second. It's based on your audio hardware. Your audio hardware could run at 44.1 kilohertz likely, or 48 kilohertz, or even 96 kilohertz or 192 kilohertz, depending on the type of audio hardware you have. It could also run lower as well, 8,000 hertz, although that's pretty rare these days. So it tells this algorithm how many numbers to produce. It's a big long list of a single number that's changing over time, and that's in the N object there. Then we have a gain control, and that gain control is set to 1. That's going to be pretty loud, so I might switch that back to 0.1. So that's going to be a bit softer. We don't want to be too loud. We don't want to go greater than 1, and even 1's pretty loud. And we've got G as the gain object there. Then we pass the N, the noise generator into the gain control, which will apply the gain of 0.1, turn it down a bit. We add the gain output into the audio context, the output there, and we start it and we start to hear noise. So let's listen. Okay, so that's noise. We can create white noise. It's called white noise, and there are other types of noise, but white noise is made up just from a series of random numbers. Applying gain, I mentioned this already, but applying a gain of 1 means we multiply the sound by 1. We multiply the numbers in that in the noise or in the periodic signal by 1, and of course multiplying by 1 has no effect whatsoever to any number because it just says it's the same. So we'll end up with values that are pretty similar. Now if we multiply by 0.2, we will turn the sound down significantly. So you can see less, if these represent increases and decreases in pressure, those increases and decreases in pressure are smaller now. And if you apply a gain of 0, you have absolutely nothing left. That is always going to be 0, and that's one way of turning off the sound. So I'll just show you that one more time. So here we have the gain. I can set that to 1. Cover your ears, this will be loud. So that's the full sound that came from the noise generator there passed to the audio output. If I set this to 0.2, I still get sound. It's quite loud. 0.1, still pretty loud. I mean, we can still hear it easily. So this shows you that gain is not linear. 0.1 and 0.01 are only 9% different compared with 1. But we still have a fair amount of sound, and the thing is, gain is not linear, it's exponential. Now if you set it to 0, you will get absolute silence. Nothing. No sound whatsoever. So that's gain. We can also synthesize tones by cycling through a wavetable at a specific rate. So a wavetable is basically a stored pattern like this. This is wavetables of 64 values, but wavetables often have more like 512 or 4096 numbers that just represent one cycle through a pattern. This is a sine wave. This is a triangle wave, a sawtooth wave. You can see it drops very fast. This is a triangle wave, and this is a square wave. You can see there's a big change there, but we stay at one value for a long time in this one. So let's have a listen to a few of these. I'm going to find this one. Glide and wave player interaction. I'm going to set the tone at 500. I'm not going to change that value, and I'm not going to set the value based on mouse Y yet. I'm going to go back and do that in a second. So this is an example that has a glide, which allows us to change the frequency. We pass that into a wave player. There's the frequency glide. And we set the type of wavetable we're using. Let's use the sine table to start with. So that's WP. So that's the wavetable player that's going to generate a sine tone at 500 Hertz. We then set up a gain to 0.1 as usual, and the wave player is the input to the gain, and the gain goes into the output there. So let's listen. 500 Hertz. Now with the glide, we can change that frequency over time. So we can set a glide time of 2000 milliseconds and change that frequency to 1000 over 2000 milliseconds. So have a listen. Okay, so that's changing over time. And we can also set the frequency based on the mouse position. Now this overrides this other one, so we'll get rid of that. And we're going to set the frequency to mouse Y, which is going to be between 0 and 300, times 4. So it's going to go between 0 and 1200 now. So you can see you can control the frequency of a tone. You're controlling wavetable synthesis. It's stepping through this wavetable here at an appropriate frequency. And you're then getting an output based on your mouse position. We can change to a square wave by choosing a different buffer here, and we'll get a different type of sound. Much harsher. But same deal.